one way we look for life elsewhere on other planets and planets around other stars is, well, not around planets, around other stars. We go to there. How do we look? We can go to these places. As you see here is pictures from the Apollo landings. We can actually go to the moon, or we have in the past, and we really have in the past. It's one issue I have with some new students in my freshman astronomy class. Some of them are under the impression we really didn't go, that it was all fake news. But we went, and I can tell you that I have myself met and I have worked with some of the Apollo astronauts. I met all of the Apollo astronauts of the Apollo 11 mission, Neil Armstrong, Buzz Aldrin, and Michael Collins many years ago. And many years ago, while I was at Grumman Aerospace Corporation, I actually worked with Fred Hayes. So if it's close enough, and again, the only place we've done this is going to the moon, we ourselves can look. Another alternative we have, where we actually go there with our robots and have either robotic landers or even rovers, and you see here examples of that. On the upper left here, this is an actual view of the surface of Titan. That's a moon of Saturn. In the lower left pictures are two images of Venus. It was only the former Soviet Union had a number of successful soft landings. None of the craft lasted very long. It's very hot and very high pressure, and so they never really lasted long. And the cameras, they were lucky to get this. In many cases, the camera melted. Literally, the camera lens would melt and be destroyed very quickly. But they were able to gather some other data. And here we see a number of successful landings on the surface of Mars. And up here, you actually see two data sets that I used in order to get my master's. I did my master's thesis on the analysis of data from the Viking lander. And these are two of the data sets that I actually used in that. And here we see another. This is the first panoramic color view of Mars that was taken by the Viking mission. So we can go to a place to see for ourselves. We can have robotic landers go. Otherwise, we have to use whatever we get, and what we get is just from the electromagnetic spectrum. That is light, and when I say light, I'm talking about all portions of the electromagnetic spectrum. Most people consider light just to be the visible portion of the spectrum. The colors we know is red, orange, yellow, green, blue, violet. And that's just the visible portion. There's also longer wavelength into the radio waves, microwaves, and infrared, and then the visible spectrum, ultraviolet, X-rays, and finally gamma rays have the shortest wavelength. So we have to get as much information as we can from the electromagnetic spectrum. And it was in the mid-1800s that chemists and others learned, with the help of physicists, that every single chemical element has its own unique spectrum. It's like having a fingerprint for the chemical elements. And this is just a neat graphic that I found that shows the emission line spectrum for all of the chemical elements. And they're all different. And that's a key thing. And that allows us to determine what chemical elements are on the surface or in the atmosphere of, if it's in our solar system, the planets that are there. When you talk about looking for exoplanets, you have to use one of a number of techniques. These are the three main techniques used. The lower one here, the transit detection of exoplanets, is also sometimes referred to as the astrometric or the photometric method. Photometric because it uses, as you see here, the photometric light curve, and you can see the planet diminish the light from that star as it passes in front of it between us and the star. We have even been able to make use of the transit detection of exoplanets here at our own observatory on campus in Fairfax, Virginia. Even with all the so-called light pollution and the like, we're able to actually have help detect planets orbiting other stars. In fact, just recently, and by recently I mean just last week, it was first participation in a peer-reviewed paper that data from our own telescope was used in the analysis of the possible number, more possibly than just one exoplanet orbiting another star very far away, so like 100 light years away. Here we see another method used to detect the existence of planets orbiting stars. This is actually the rarest method and the most difficult to use, called micro-lensing or microgravitational lensing. And the micro-lensing is an effect that we learned about really from Einstein's general theory of relativity. And so it takes quite an effort to detect that very slight lensing effect. That is, gravity bends the light just like a lens does, and it's always called the micro-lensing effect, and can tell us about the existence of a planet between us and the distant star. The other method, and really the one that was first used, is called the Doppler shift or radial velocity method, and that makes use of the spectra from the stars, and we see that the spectra changes. And Doppler shift, just like with the Doppler shift of sound waves from a train whistle, if you're standing on a platform and you hear a train coming, it'll sound higher pitch as it approaches the station, and if it's just going to keep going, it'll sound lower. So it's like, yeah, so you hear that whistle blow from higher pitch to lower pitch. And similar effect occurs with light. Light's apparent wavelength or frequency is changed as it's approaching you and as it moves away. So stars will have a wobble. They don't just sit still. Everything's in motion in the universe. But the planets orbiting the stars cause it to wobble in its motion, and we can detect that wobble with the help of the Doppler shift. So those are three main methods. So what about looking for life in our own solar system? Our favorite places, talk about Mars, and I already did, but there's also a large moon of Jupiter called Europa. It was originally discovered by Galileo, in fact, in 1610. And Europa, we know, is completely covered with water ice. And the way we know that it's covered with water ice is because the spectra of the light from the sun reflecting off the surface of Europa has the absorption lines indicative of H2O, or water. So we know it's almost completely water on the surface. It's frozen solid. There, of course, are cracks and fissures created by all kinds of motions and gravitational effects. But if there's water on the surface, there's a very good possibility that there's liquid water beneath. And we had planned a mission many years ago to go to Europa to give us primary evidence that it is a liquid beneath this solid surface. That mission hasn't flown yet. They're talking about it now for like possibly starting that up again in 2022 or 2023 as a mission to Europa. Nonetheless, as anyone who knows, in states in our country, like Minnesota, you do ice fishing, you drill a hole in the water and you can go down and it's liquid and there are fish there. So the big question is there anything living in the liquid water beneath the surface of Europa? And hopefully someday we'll find out for ourselves. Here we see the inner planets in our solar system: Mercury, Venus, of course our own Earth and Mars. And what are the common features of these? The four innermost planets, as you see, are small compared to the large or Jovian planets. but they have high density of material. In fact, that's one thing the Earth is #1 in. That's the most dense planet in the solar system. With rocky surfaces, we always like to look towards and we call them terrestrial planets. And again, how do we know what they're made of? Whether it's Mercury, Venus, our own Earth, we can go to and get samples, or Mars. We again use these spectral lines telling us what the surfaces are composed of. With the Mercury and Venus, we had the Soviet Union had successful landers on Venus, and with Mars, we actually had landers, of course, and rovers as well. Within our own solar system, again, where we're looking, the Jovian planets, the large gas planets, Jupiter, Saturn, Uranus, and Neptune. And remember I said density is what the Earth is #1 at. And as far as densities, if you don't know some of these numbers, take a look at the density of Saturn. It's less than 1,000 kilograms per cubic meter. What's the magic there? Well, the density of water is 1,000 kilograms per cubic meter. And that determines whether or not you're going to float or sink in water. So if you had a bathtub magically made large enough full of water, Saturn would actually float in that bathtub because its density is less than that of water. All of the Jovian planets, Jupiter, Saturn, Uranus, and Neptune, are much larger than Earth, Jupiter, of course, being the largest. But they all have relatively low densities compared to those terrestrial planets. And the major chemicals found, as you see, composed primarily of hydrogen and helium. And again, how do we know that? We know it from spectroscopy. And so here you see top 5 elements in the atmosphere of Jupiter. And again, it's dominated by hydrogen with some helium, even carbon, nitrogen, and oxygen. Saturn also mostly hydrogen, helium, carbon, nitrogen, and oxygen. A little different there, a little more impurities, you might say, beyond hydrogen with Uranus and Neptune. Again, it's not just the planets in our solar system that we look. There's also the moons. I already mentioned Europa. But some of the moons are even larger than official planets. Ganymede and Titan are actually larger than the planet Mercury. And as we said, Europa is completely covered in water ice and may well have liquid water beneath, but we need some primary evidence for that. And Titan has a uniqueness of being the only one in the solar system, the only moon orbiting a planet in the solar system that has an atmosphere, a substantial atmosphere. And that atmosphere, by the way, is mostly nitrogen. And originally, until we had, 2007, when we had the lander go and lands on Titan, we thought that atmospheric pressure was actually equivalent to Earth's atmospheric pressure. Turns out to actually be almost twice as much as atmospheric pressure. But again, it's almost all nitrogen. There's no free oxygen, so you wouldn't be able to breathe at all. And that's our neighborhood in our own solar system. So if you want to give me some questions that you may have now, I gotta see. Your mic's muted, Julia, so for me to hear. Somehow I've lost the...
That's right, sorry. There were a lot of questions, just a second. Let me make, but we also had some turmoil in chat today. So some people were going really off topic. So here we are. How do we know, just a second. How do we know if it is possible, if the possible other life forms are trying to find us or not, from Tori Porat? Question number
well,
one.
why, in this part of the talk so far, I've just looked at how we examine planets in our own solar system and how we're looking for life there. In the next part, I'll get more into how we're looking for life elsewhere out there and how we know whether or not people are trying to communicate to us. So if that's okay, let me get to a little more of my talk before I get to other civilizations trying to communicate with us.
So another question was, why did we send Voyagers? I know some people here already know, but some people are new. So maybe just a little bit.
What was that? Why did we send Voyager?
Voyagers, yes.
Yeah, the Voyager 1 and 2 were meant to be a discovery craft. I mean, it was the first time that we sent a craft flying by Jupiter and Saturn. And with Voyager 2, they were able to use the gravitational assist from Jupiter to actually point that towards Uranus and Neptune. So I was able to see Jupiter, Saturn, Uranus, and Neptune. And you get up close images that you cannot get from ground-based or satellite-based telescopes. And also you get better, what we call high-resolution spectroscopy. And in some cases, for example, Voyager 1 was sent on a particular trajectory that literally went through the rings of Saturn and also demonstrated that, gee, it's not solid rings, but just a bunch of hundreds, thousands of particles around Saturn. And by the way, they're mostly water ice, frozen water. And the way we know the water is, again, as spectroscopy, knowing the chemical composition of the material. So Voyager 1 and Voyager 2 were the first times we went to the outer solar system to get a flyby of these Jupiter and Saturn. Voyager 1 went Jupiter and Saturn. Voyager 2 was able to go, excuse me, Jupiter, Saturn, Uranus, and Neptune. So we learned a lot from having a spacecraft go by. It's just like the New Horizons spacecraft to Pluto. And 2015, that was the first time that we had sent a spacecraft so close that flew by Pluto, and we were able to learn a heck of a lot more, getting better images, getting better spectroscopic data, so we can learn a lot more about the planet. Also, we can actually even tell about the planet by how it affects the trajectory of the spacecraft. So there's a lot to learn.
We have, let me read you some questions and then you decide which ones you want to answer now and which ones you want to answer later. So I'll just read some of them. How easy it is to fly to Titan? Which moon has the best promise for life search?
Okay, let me,
go ahead.
I'm going to forget otherwise.
Okay.
I'm getting old, my memory is not as good as it used to be. It wasn't so difficult to get to Titan. Remember, Titan is the moon orbiting Saturn. Saturn we got to even with Voyager 1, which lifted off, 1976, and got there about 10 years later. The big thing with the Cassini spacecraft that went to Titan and dropped the lander is the fact that it had to get there at a particular trajectory so that it could be captured by Saturn and its moon Titan. What are the best possibilities of life on moons? Again, I've mentioned two already. Titan, which is the only moon in our solar system that has a very substantial atmosphere, and Europa, where you don't expect any life on the surface. It's totally frozen water ice. But we do expect that the liquid water beneath the surface that we expect to find may contain some life. So those are two of the best candidates. What else do you have?
So, what is the most promising moon to send the probe to search for life?
Well, I think, again, it's either
mhm.
Titan or Europa would be the best moons to search for life. A lot of people now want to go. It's easier to get to Jupiter. So it's Europa orbits Jupiter. It's closer. And I certainly, again, there was already a mission proposed to go to Europa. And I'd certainly love to see that fly in my lifetime.
Can we terraform Europa on Titan? People ask.
Terraforming. That's funny. I teach a course in astrobiology. We talk about terraforming Mars, and it's nothing easy. To be honest, the most realistic would take at least 100 years, perhaps many more, in order to terraform Mars, and that is a lot closer and has a lot nicer conditions than either Europa or Titan. To terraform either one of those, because they're further away, Europa orbits Jupiter. Jupiter is 5 times the distance that the Earth is from the sun, which means it receives 1/25th the amount of light. So that's a lot of problems. And Titan orbits Saturn, which is almost 10 times. So that receives 1/100th the amount of light. So it's going to be a lot more difficult to try to do anything with photovoltaics or solar energy when you're that far away. So again, realistically, it would take 1 to 2 centuries, 1 to 200 years to even under the most ideal situation terraform Mars, and that has the best possibility.
I just missed one question that people wanted to ask. Do you think that in a different universe there might be life? I think this is where you are getting, right, with
well, I don't
the next part.
Yeah, maybe I should just start my talk. And I don't know if you really mean a different universe, but if you mean a different solar system.
That's right. So probably let's continue with the presentation now. You may want to, yeah.
Got it. That part I got. All right. So how do we look for other planets? Again, we started in the mid to late 1990s using the radial velocity method, seeing the change in the spectral lines of certain chemical elements from the distant stars, and realized that they were being affected by planets orbiting that star. It was then roughly 2000, and I think I have it on here, when the launch of the Kepler Space Telescope in 2009 was the start of our main use of the transit method or eclipsing method, because that planet gets in front of the star just like my finger gets in front of my face, so you don't see the whole face. And since we've had that, and the Kepler Space Telescope, by the way, if you look at my slide here, you see it only looked at one portion of the sky. And boy, it discovered a lot of possible candidates, we say. Because in science, just because one observation may make a detection, that's not good enough. It has to be reproducible. So the Kepler Space Telescope gave us thousands of candidates. And using both ground-based telescopes like ours at Mason and elsewhere, we look for verification and validation of the data. And to date, there is officially recognized over 4,100 planets orbiting other stars. The International Astronomical Union is the official body that tells you how many there are. And I forget what it was the last time I looked, like 4,400 even, most recently. So the Kepler Space Telescope was looking in that small portion of the sky for about 9 years. As you see, it began collecting science data on May 12, 2009, and it had to be shut down largely because of the gyroscopes that keep it stable and allow the pointing. It went up with, excuse me, there's two sets of 3 gyroscopes. Each gyroscope was duplicated, one for each axis, and they had duplicates go up. So for a while, when one failed, the other one would come into play. Remember, a gyroscope's always got to keep spinning. Once it doesn't spin anymore, it's not useful. So for a little over 9 years, we were collecting data and finding candidate systems that had. Today, there is a satellite, of which one of my colleagues is a co-investigator on. And TESS, I should have put what that stands for, but that's the Exoplanet Survey Satellite, TESS. And instead of looking in one place, over the period of a year, this satellite is able to hit a large portion of the sky, except as you see here, just at the top, the north and south polar region. But it maintains a orbit, and it moves in its orbit, we call precession, and so it's able to look almost everywhere in the sky. Again, it uses the same transit method, but here we're looking more broadly in space all around, whereas with the Kepler mission, it was just one. Future missions that should help us, as you see here, the Webb Space Telescope still hasn't gone up. I remember when it was supposed to launch in 2018, that's come and gone. Now they're talking about March 2021. And the advantage of the Webb Space Telescope, that's different from the Hubble Space Telescope. It's going to have a mirror much larger. The Hubble Space Telescope had a mirror that's roughly 8-foot diameter, but James Webb Space Telescope, and you're talking about 6 times that, but it's segmented, so it's going to open up in space. And unlike the Hubble Space Telescope, which was able to see from the near UV to red as far as light, the James Webb Space Telescope doesn't even see the color blue. It's going to be range of wavelengths from roughly orange, red to infrared. And the key thing there is, turns out the spectral lines for water are in the infrared. And for us to see the infrared in the atmosphere of planets orbiting other stars, you are best counting on the James Webb Space Telescope. And there is what's called the W-FIRST telescope, and that one is actually designed to actually take images of planets orbiting other stars. So there are future missions that we hope to learn more about planets orbiting other stars. Now, and this was a question before, people talked about, what about intelligence signals, signals that intelligent civilization might put out into space. And I'd like to remind you, in a way, even though we didn't know it, we've been putting out radio signals into space since the late 1800s with Marconi and the very first radio telegraphy, radio waves going out into space. And one of the reasons that radio waves work so much better in trying to get into deep space is the longer wavelengths of radio waves allow you to penetrate, as you see here, in particular dust clouds. There's a lot of dust between the stars. They scatter blue light. In fact, right now, you can see, behind Julia, I should say, not on my screen, is what's called a reflection nebula. And it's blue. Well, it's blue because of scattered light. In fact, that's why our sky looks blue. It's because of, it's called Rayleigh scattering, scattered light. So blue light can't penetrate these dust clouds very well at all. They easily get scattered. And red light penetrates better, but infrared even better, and it's able to go the most distant. Excuse me, not infrared, but beyond infrared. You get into microwave, you get into radio, radio can penetrate dust clouds the best of any of the electromagnetic spectrum, of course. So whereas you are unable to see beyond those reflection nebula behind Julia right now, with radio waves, it penetrates those emission nebulae and the reflection nebula and can actually get to the more distant objects. Also, it turns out, making radio transmitters is a little cheaper, and part of that is, you need, how much energy are you going to put into this? With radio waves, they're the lowest energy waves, and we're able to make those more easily. It takes a lot more energy for us to make the higher energy electromagnetic spectrum. On the upper right of this slide, you see the largest radio telescope in the world. It was literally carved out of a mountain in Puerto Rico. It's called the Arecibo dish. We can't move that mountain, of course, but we can move the receiver that you see just hanging above it. And we can move that a little, but you are limited to mostly what comes within the point of view of that mountaintop. And then again, what we talk about radio waves, or what wavelength, and that has to do with the penetrating capability, that is penetrating even our own atmosphere. You want to communicate with radio also because radio waves can even get through the clouds on a cloudy day. So what will get to us the best, and this gives you an idea down here of the range. And by the way, you see hydrogen and hydroxyl, J convenient. So we're able to see the lines, the emission lines of hydrogen and hydroxyl, or H2O, and you can actually look in that wavelength or frequency. There's also, of course, the matter of, again, what are the, as it says, beacon frequency, hailing frequency. It's those that can penetrate the most. And what natural wavelengths are there? What wavelength do you choose? The one that penetrates the most, the one that one civilization may know the most about. And as you see here, neutral hydrogen, which has a wavelength of 21 centimeters, or frequency of 1420 1.42 gigahertz, or 1420 megahertz. It's something that any civilization that exists out there would know about, and it's a specific wavelength you could use as your center frequency to then modulate and actually send a signal. There are some that prefer to use the 1.7 gigahertz, and that has to do with the hydroxyl line, again related to, if you have water that you use, and you have water on your planet, you'll know about these wavelengths. There are other so-called magic frequencies, but the ones that we concentrate on are the ones that I just went over. And then when you're dealing with frequency modulation, how are you going to determine the bandwidth? That's all something that we have to work with. So the wavelength we choose have a particular bandwidth that we're going to look. And you see here a typical, this was a project that ended only recently, the end of last year. It's called SETI at Home. It wasn't done from radio telescopes on home computers, but they developed this distributed processing system that would allow a person on their own home computer to actually work with the data from, of all things, that large Arecibo telescope, and see if they can find any modulated signals within. And as you see here, they would use a bandwidth 2.5 megahertz centered on 1.42 gigahertz. And you're looking at that bandwidth. So, and this gives you an idea of what you're looking. Okay, you have the signal. We're looking at a particular portion of that signal. Can we see that there's a signal within that wavelength that tells us that there's intelligence behind the signal. It was back in 1960 at the National Radio Astronomy Observatory in Green Bank, West Virginia, which isn't too far from where I am in Fairfax, Virginia, actually. And a group of astronomers led by, as you see there, Frank Drake, carried out the first attempt to detect radio transmissions from a distant civilization. And again, they were looking at that 1420 megahertz or 21 centimeter region of the radio band. And, you know, they didn't detect anything, but of course that was just one. There have been many attempts since. And there have been some unusual signals, but none that have been discovered again. As I said, one detection isn't enough. In 1974 was the first time we sent a signal out into deep space from that very Arecibo telescope, radio telescope. Again, it was designed by Frank Drake and Carl Sagan. There was a lot of, you can read up a lot on this. To the right here is a diagrammatic representation of the bit stream and how the civilization is supposed to receive it. In my astrobiology course, I give my students the bit stream. I said, okay, here's a signal that was sent out to this globular cluster 25,000 light years away. Of course, that also means it'll take 25,000 years for the light or the radio waves to get to them. You know, how would you interpret it? And almost none of the students ever come up with the proper scheme. So you've got to be careful what you're dealing with. Another famous radio telescope that existed for many years, as you see, 1977 to 1997, was nicknamed the Big Ear. You see how this is a more linear array of antennas, a linear antenna, basically. And they were looking, as you see, this is the famous signal that was discovered August 15, 1977. The problem is, even though it was, as they call it, the wow signal, pointed in the direction where that signal came from, they never discovered anything else. So it may just be some transient signal or even some background noise or something else. As you see here, if you're wondering, that site is now a golf course. No more radio experiments there. If you want to know where that was coming from and where that signal came from, the wow signal, it was in the Sagittarius constellation. Those are the details of it. And again, there were 50 follow-up searches and never a signal detected from that same region. There are other projects. This tries to go through some of them, the ones that have been around the most and those that haven't been around as much. But as you see, we've been looking for radio signals from other civilizations for many years since, and we've still not detected any signal that has been duplicated and verified. And this gets into a little more detail about the Serendip project, which uses a system designed by UC Berkeley, and it makes use of the large radio telescope in Arecibo. The SETI at home, which, as I said, actually has ended now, allowed you to download software to your own computer and do some of the processing as part of a parallel processing. This goes into a little more of the details there about how we're able to pick out a signal and then focus in on that signal and determine or report it, and then determine if there's anything else that's found. A big benefit of this SETI at Home project was actually the software that was developed so that people could participate in a parallel processing effort across the entire world. And while originally it was developed by Berkeley to use on this SETI project, It has been used, as you see here, for protein analysis, folding of proteins to predict certain proteins and the like, and also used by the University of Wisconsin to do analysis of the gravitational wave detection using the LIGO detector. There's also the Allen Telescope Array in California. And look how long things take time here. They had 42 dishes available in October 2007. They lost some funding, then it was restarted with additional $3.6 million, 2012. And most recently in 2017, just 3 years ago, it was upgraded, and it still is in use, using many individual telescopes, radio telescopes, as you see, originally 42, and it's been upgraded. How many of the ones do I say? To include more radio telescopes. You can make radio telescopes all look at the same location, and having many smaller radio telescopes work as a single large dish. Now, since then, there's also been talk about using lasers, or laser detectors in this case. Optical SETI is where we're looking for laser light. And what's laser light? It's light of a single wavelength or frequency. Often a laser, the laser pointers, will be of a specific wavelength. You know, I have one, my green laser pointer, it's 560 nanometers, that's the wavelength. And so you can make use of that as, in a sense, the carrier wave for your signal. And there are some who think, well, you can transmit a lot more information with a laser. And of course, there are other problems with lasers as far as reaching so far a distance without worrying about all the material in between us and them. And then don't forget about the atmospheres that they may deal with. So there are still other programs looking at both using lasers to send out information and also lasers to receive. Again, I talked about the fact, gee, that very first message, how did they come up with that encoding scheme with a series of zeros and ones in the message was supposed to be laid out in the kind of pictograph and then transmit the information from that pictograph. This gives you an idea that it's not such an easy thing to come up with these codes. Often we use a cipher and encoding device that is based upon some prime number. That's why you may hear, gee, all these engineers and encrypting engineers, they like to get with these prime numbers because they allow us to encode a lot of messages. As far as listening for things, again, remember, we started about 1960, and we've been trying to listen for radio waves and now others, and we haven't found anything. But that doesn't mean that there isn't anything. Don't forget, if we've only been looking for the past 60 years, it's radio waves or other electromagnetic radiation that's within a 60 light year sphere of radius of a sphere. And, you know, there's may not be something within I mean, the nearest star is over 4 light years away. There really are only something, you know, a few dozen stars within 60 light years. So as you see, as it says, there aren't many stars that have been observed yet, and not many frequencies that have been explored. And again, you know, what did we do when we did send out spacecraft? Someone had asked about Voyager 1 and Voyager 2. Voyager 1 and Voyager 2 had what you see to the right here. Many of our younger people online may not even recognize this. This is like a long playing record, an LP, if you know what a record player is these days. And back in 1976, when the Voyager spacecraft was launched, it created this metal-based and it looks like there's gold. It is actually gold plated, because gold is able to last a long time. And there are instructions on one side engraved with instructions how to make a LP record player. And as you see here on the record, they actually included sounds from Earth, and they encoded pictures. On the Pioneer spacecraft, which was about, I don't know, about 8 years earlier, well, it was in the late 60s, got out to Jupiter back in Pioneer 10 and 11. Always 2 spacecraft got out there in, what, about 73, even though it was launched in 68. And the like, and all they did was have a gold-plated plate with this engraving, and that's supposed to tell you about the hydrogen atom and that we're the 3rd planet from this star. By the way, they had Pluto back then too, still. And we're humans compared to the size of the Pioneer spacecraft. This is Pioneer on the left. The Voyager spacecraft contained this. And what if the silence were broken? Again, if there is a signal detected, we want to be able to detect it again in order to interpret it. And we actually do have a treaty at the United Nations that tells all the signatories, all the countries that have signed this treaty. And you see here, in case the signal is detected, you're supposed to verify the authenticity that it is from somewhere else, contact the International Astronomical Union, the IAU, which will then contact the United Nations, inform the governments, not only of your country, but a general announcement, and then make an announcement to the public about it. So no one knows for sure what kind of successful detection of an intelligent signal may have on our society, but I don't know that it's all as much as some people think. And if I can just quickly go through the conclusion, then I'll take more questions. Lots of planets have been discovered orbiting stars in our own galaxy. As I said, officially, there's over 4,400 exoplanets, stars, planets orbiting other stars. Some of these, we've been able to get some spectroscopic data, and we know that there is water in the atmosphere of some of these. We've discovered water on planets in our own solar system, and we know that there are many galaxies out there beyond our own. Of course, Hubble Space Telescope leads us to believe, based on just the sampling of the sky that it's looked at, that you're looking at, 200 billion galaxies at least. And like our own Milky Way, they can contain anywhere from 100 to 400 billion stars within each. So that universe, of course, is large, and there's a lot of possibilities of systems around it. But as I point out, science is the only way to determine this. On the downside, we see about 1% of the exoplanets that have been discovered are in the habitable zone. And that habitable zone is where liquid water can exist on the surface of a planet at a distance from its star. And only about 0.3% are Earth-sized. So as we've gained a lot of data, we still see the Earth seems to be rather unique. And also note, just because you have water doesn't mean you have life, but we believe that there is at least a better possibility of it if you do have liquid water. The Fermi paradox is something that was first questioned by Enrico Fermi, a famed nuclear physicist. In the early 50s, he was supposedly having lunch with some astronomer friends of his, and he said, you guys talk about possibility of life. But if there really was intelligent life out there throughout the galaxy, and he's just talking about the galaxy, wouldn't we have detected it already? And there's a logical argument. I have a whole lecture on that I go over with my astrobiology course. And he sort of demonstrates that life should be able to populate the galaxy pretty quickly relative to the development of life on a planet itself. We know that it took a couple of billion years before life developed here on Earth. Using calculations that Fermi did just on the back of the envelope, you might say, he demonstrated that there ought to be a lot of planets and stars within our galaxy already with intelligent civilization if just one started expanding. You also have to know, a lot of people talk, well, there's a lot of other galaxies out there. Each and every second that we speak, the universe is getting larger and larger. That's expansion of the universe first established by Ed Hubble. And at the same time, I do want to point out, we are not at the center of the universe. It doesn't work that way at all. Wherever you are in the universe, by the way, I teach a course in cosmology as well. Wherever you are in the universe, you can't point to a central region. I use the analogy more of a balloon. Think of your universe as the surface of a balloon. You can go backward, forward, left, right, but you can't go off that surface. And the center of the balloon is actually not on the surface of the balloon. So you're going to have an expanding universe where we can't point to the center, like the two-dimensional creatures on a surface of a balloon can't point to the center. So why don't we try to get some questions before we time out? Unmute your mic, Julia, if you want to. Oops.
You're right. Thank you. I was saying that we got lots and lots of questions here. So the first question was, if we go a bit up, a lot of people asked about the wow signal, if we know, if we could make any sense out of it, or it was
No,
just...
it was just a very brief modulation in the center frequency, and there's been no other signal coming from that region in that portion of the radio spectrum since. So it's likely to have been a transient type signal caused by so many things in nature can get between us and that region of the sky out there.
So another question, what if the intelligent life haven't learned how to use radio waves?
Well, then by definition, we wouldn't be able to detect that they exist unless we go there. So you are looking, we basically define an intelligent civilization of one that has achieved the ability to communicate with some portion of the electromagnetic spectrum.
So does it mean that all intelligent life use symbolic logic? The question asked.
Well, I mean, it's, we can get into a discussion here about what's intelligent life. I think my dog's intelligent, but on a different level. And he may even be able to count. I often think he's able to, I give him certain treats, and if I don't give him at least a top number, he seems to know, oh, he's due more or something. I don't know how much he counts, but a truly intelligent life form would be able to work out numbers. And yeah, there is in mathematics, I'm not going to get into number theory, but there's been a lot of work in number theory. If you're an intelligent species, you are going to know mathematics.
Some people are asking about the golden record. They say, what if aliens are blind or deaf? Why do we assume that they can see in the same light spectrum or hear in the same, the same sounds that we do?
Well, any life form has to have senses. And, for us, we see in the visible portion of the spectrum because that's the portion where we get most of the light from the sun. So even if there's another civilization out there that's blind to visible light, they're going to have to be able to see. And by the way, if they're orbiting some star, it's going to be based upon what light that star is putting out. And we are able to go throughout the spectrum to reach any of stellar output.
So another question is about your slide. It is, what is the Hawking versus Geller thing in the corner?
Oh, that's fine. That was actually a graphic made by a art student here for a talk that I gave about statements made by Stephen Hawking back in 2010. So we set up a virtual debate. Back then, we didn't have Zoom or any of this back then. And yes, Stephen Hawking was aware of that. I disagree with his conclusion about whether or not we should be sending out a signal to other civilizations, because he was concerned. In fact, if you look on the other side here, this is from a Twilight Zone episode where it was called To Serve Man. And they discovered this book. They were only able to translate the title of this book by the extraterrestrial intelligence. And at the end of the episode, you find, oh, they weren't looking to help human beings. They were looking to cook human beings to eat. So that's a whole nother story. But Stephen Hawking felt that just like with Columbus coming to this hemisphere, it wouldn't fare well for the people originally here, as it didn't fare well for the Native Americans here. But I point out the fact that you were dealing with the same species. Native Americans here and Europeans were of the same species. The likelihood, and I even published a paper that did this analysis, the likelihood that another species on another planet orbiting another star would have the same exact biochemistry of us in order to actually make use of us for food is rarer than winning that big lottery. In fact, what did someone tried to say, well, can you put it in terms, I think it would be equivalent to winning that, 1 in 200 million lottery 3 times in a row. It's extremely unlikely.
So another question is, especially now with all the pandemics going on, is it possible that human beings can get infected by extraterrestrial microbe? Or are we so different that it is not possible?
That's the basis of a book called The Andromeda Strain, right? A science fiction book. But once again, I go back to the equation that I developed in this paper I published on the likelihood of the biochemistry being the same. It is really extremely rare. The reason why COVID-19 is so successful is it's been on this planet even longer than we have, all right? So it's gotten used to human beings, and the most recent strain, as they call the novel coronavirus strain or COVID-19, has developed a way around our immune system. You're actually exposed every second, every minute of the day to viral particles and bacteria and everything. Your body has built an immune system that is able to destroy most of those creatures. It has taken the coronavirus so long to develop a way around it that we don't have any natural immunity to that, and hopefully eventually we will have a vaccine. But again, the different types of coronaviruses have been around, and it's actually come across a mutation of the coronavirus that has been so successful.
So do you have some more time for the questions? Or
yeah, I can take a few more questions. It's fine.
Okay. So let me see what else we have there. The question was, I'll probably just restate it. In videos, aliens are mostly like humanoids, but do we actually expect the extraterrestrials to look like us?
Only if they evolved on a planet just like ours. And that is actually not so likely. As I said, it's got to be the same exact conditions taking place. And then you develop the same type of senses, same type of biochemistry and the whole bit. So I don't think we think extraterrestrials would be just like us. That's really far-fetched. And in fact, that's part of my point with originally my debate or disagreement with Stephen Hawking. And part of the, let's see, I wrote a chapter for this book called Extraterrestrial Altruism. And the chapter in this book is the predecessor to the article that I wrote about it. Oh, and here's the chapter, if you were interested in seeing, just says, harmful extraterrestrial intelligent hypothesis denied. That was the hypothesis put forward by Stephen Hawking. And my view was actually, if any extraterrestrials ever come to the planet Earth, they're not likely to be belligerent, but probably to be more altruistic.
So we have a question. Is there a type 4 civilization in the universe?
Excuse me, is there a what?
Type 4, you know, on Kardashev scale. So we are not even type 1. So.
Oh, we don't know of any other civilization at all, regardless of the type.
So. Okay, I guess this is about it.
Okay. Thank you all for listening, and I hope you learned something here. Be safe and be well. Right?
Thank you so much. And people say thank you in chat. You probably see that.
Yeah, now I'm seeing the chat, and I stopped sharing the screen.
Yes.
Okay. Have a good day, everyone. I still got lots of term papers to grade and read.
Thank you, everyone. Thank you, Dr. Keller. Thank you. Goodbye.